So let's take a look at continuity, or what it means to be continuous. And again, this is something that we use to describe a particular function. And I think maybe the best definition is just to say that it's completely connected. And let's take a look at some possible graphs here. So let's take maybe just a general cubic function. It would look like this. See how I could draw the whole thing without lifting up my pen? I could take a square root function. So zip it over. I could look at an exponential function. I'm drawing all of these without lifting up my pen. I could take a logarithm and draw it. I could take a sine curve and I could draw the whole thing. I could look at an absolute value. Everything is nice and continuous. All of these are honestly a little boring to talk about when you talk about continuity because they are all continuous on their domain. Now I realize that a square root function isn't defined for negative x values, but on its domain, it's nice and completely connected. Logarithms are the same thing. I understand there's a vertical asymptote here, but on its domain, it's nice and smooth and connected. All polynomials, doesn't matter with a cubic or a quadratic or just a line, they're always completely connected. It's probably easier to talk about continuity to look at, well, when is it not continuous? So where is it discontinuous? So problem areas. Okay, so what can happen? Well, you could have a hole, you could have a jump, or you could have an infinite discontinuity. And those are the three I really want to talk about because they're the most popular. Discontinuity. Okay, they're pretty easy to draw. You can have a hole that would look something like this. And again, there's no way you can draw that without lifting up your pen. You could have a jump that would be like a piecewise defined function where you're here and all of a sudden, boom, you pop up there. And then you could have an infinite discontinuity, which is just like a vertical asymptote. So we could have an issue there. And so we would say something like, it's continuous everywhere except, maybe x can't be 4. It's continuous everywhere except, let's say that x value was 5. And it's continuous everywhere except x can't be 3. It's honestly, now here this isn't a domain restriction because you can find the x value that corresponds to 5. Even here I could do this. I could put this here and define the function at 4. It's still not continuous at 4. I still can't draw that function without breaking, going up there, and coming back. Okay, so let's think about the formal definition. The formal definition, so the more formal way, to talk about continuity is to say that the limit of the function as x approaches a has to equal the function's value at a. So I guess we can say that for it to be continuous, first of all, it has to have a limit. Right? You see how this example, the limit doesn't exist? Well, of course that's not continuous. You're going to have to jump. Here, the limit actually exists. If I come in from the left side, and I come in from the right side, and I really, really approach 4, I still have a limit. But the limit, L, does not equal the function's value at that point. Even if you took away the dot, then the function wouldn't be defined there, and it still wouldn't be continuous. It's not completely connected. Okay, so what we're saying here is the limit L has to equal the function's value for it to be continuous at that point. Okay, so let's take a look at maybe another example. So we could have some graph, or maybe the graph would look like open circle, continue this way, close circle, and then down here. And you know what? Let's define this here. So there's no domain restriction. Our function f is defined on all x values. If you want to know what, let's say this is -2. F of -2, I don't know, it looks like 1, 2, 3. F of -2 negative 3. What's the limit of our function as x approaches negative 2? Well, that's positive 2. Again, if you look at what we're doing, the limit is the y value that it's approaching coming from the left, coming from the right. That's 2. The function's value at negative 2, well, that's down here at negative 3. The limit does not agree with the function, and so it's not continuous. There's no way that you can think that's completely connected. Same thing down here. This one happens to not even have a limit. At least the limit exists at negative 2. The limit doesn't even exist at, well, 1, 2, 3. The limit doesn't even exist at 3. So of course it's not continuous. And again, it's not connected. Okay, they do like this problem. Let's define some piece. Instead of looking at some graph, let's look at a piecewise function. So let's look at 4x plus a and negative x plus 3. And let's define over here, this is when x is less than or equal to 1. And this was when x is greater than 1. Okay, so what we want to do is we want to pick a value of a to make this function continuous. Now remember, this is going to be some piecewise function. So it's going to be some line, and that's going to be a different line, and we want to make sure it's completely connected. So what do you want to do? Well, we just want to make sure that the left y value equals the right y value. And again, we don't have to check this function or this function. We only have to check the break. Only at x equals 1 is it interested. Again, at x equals 1. Though this is just a line and this is a line. They're going to be fine on their own, but at the break, there might be some jump. Okay, so what is the left value when x is 1? Well, that's just plugging a 1 into here, and we get 4 plus a. That's the left side. And the right side is just plugging in 1 to there, and we get 2. And so we know that this equation is solved when a equals negative 2. So if a equals negative 2, we guarantee that the left y value and the right y value are the same, and then they meet up. And if they meet up, they're going to be connected. Think about what this is saying. This is saying that this needs to be 4x minus 2 is going to meet up perfectly with negative x plus 3. And if you look at the graphs of this, okay, the graphs of it is going to look something like this. And this is the point 2, and look what the top function is at 2. 4x, the top function is 4x minus 2, and we're looking when x is 1. So if you plug in 1 here, you're going to get 1 comma 2. And then you stop being that function. Well, now you start being this function, but you plug in 1 to the top function, and you're still going to get 2. So check that out. Boom. If you graphed it on your graphing calculator, that's what you'd look like. And again, this is a nice connected curve in that I can draw the whole thing without picking it up. So I picked the exact a value. Any other a value is going to shift this blue up or down, and then there's going to be a jump there. Okay, so this is one of the best things they like to do, to talk about continuity. After that, again, you really go back to deciding about, well, where's their problem areas? Again, problem areas are holes, jumps, infinite discontinuities. And how else can that happen? Well, again, we can look at vertical asymptotes. What if I just looked at y equals 4 over x minus 3? That's going to have a continuity problem. And really, it's got a domain restriction. X can't be 3, and that's kind of the same idea of talking about where there's an infinite discontinuity. That's as a vertical asymptote. Now, how do you get a hole? Well, that's a little bit different, but not too bad. You can look at x squared minus 9, and let's say x minus 3. This is going to look just like the line. Again, if we factored this, it'd be x minus 3, x plus 3 over x minus 3. And we can cancel these as long as we promise to never let x equal to 3. 3 is still a domain restriction. And so really, if you graph this on your calculator, it will look just like x plus 3. And x plus 3 is this line here. Except there's going to be a hole at 3. And again, you can take a look at how some of these problems occur. But holes, jumps, infinite discontinuities, certainly piecewise defined functions are going to be problems.